All right, this is week number 3. This is our lesson. We are doing more logic gates this week. We're going to learn some new logic gates we're going to apply in the lab. We're also going to learn a little bit about what TTL means and logic levels, and we're going to talk about some of the lab components that we use as well. So here we go. Figure out how to advance my slides here. So that is our topics for today. We're also going to do some problems at the end too for practice. So one of the neat things from the very first lab, you may have noticed 3000 converted into hex. So 3000 decimal, convert that to hex. The answer is BB8. I wonder if that's a little inside joke from the Star Wars community there of where the name BB8 comes from. All right, comment on assignment number 1. So that was the conversion assignment. About the average was about 29 out of 35 for that assignment. There were 6 people that did not submit anything. So I have connected with those people, or at least attempted to connect with them to see what went wrong, whether it was a technical problem or whether they just didn't do it. In general, if you don't do your assignments, I really don't care about that. I just want to make sure there's not something that's preventing you from doing those. But it is up to you to actually submit your assignments. If you choose not to, that's up to you. Just be aware that you are losing marks by doing that. All right, so we talked about logic gates last week. We did the AND, the OR, and the NOT gate, or the inverter. This is what they look like. We talked about how you could do a Boolean expression for each one. So that's the expression for an OR. This is an AND. So the asterisk means AND. The plus means OR. And anything with a line over top of it, that means the inverse of that signal, or a NOT. We talked about some terminology, so on or off, high or low, true or false, 1 or 0. Those all mean the same things, interchangeable. So on can mean the same as high, true, 1, or yes. For the AND gate, we talked about with each of these gates, we have a truth table. And that is basically all the different permutations of inputs you can have and what those inputs would give you as a result. So this is the truth table for the AND gate. So basically if you have a 0 and a 0, you're going to get a 0. 0 and a 1 gives you a 0. A 1 and a 0 gives you a 0. And a 1 and a 1 will yield a 1 for an AND gate. So that's the OR gate. You should understand what the truth tables are for each of these and be able to identify the basic ones. And the NOT gate. Pretty easy to identify. It's only got 1 input on the NOT gate. And we also talked about how you can have multiple inputs on gates as well. So this is a 3-input AND gate. And we will use gates that have up to 4 inputs in our labs this semester. So gates are not useful on their own. We want to combine them together to actually create something that is useful. So this is a combined set of gates to make a circuit. We can express this by coming up with a total Boolean expression here. So we have an A, here we have a B, here we have signal C. So B goes through this and becomes not B. A and not B together. We're going to AND those together. So that becomes A and B not. This becomes, or B bar we'll call it, B bar and C. B bar and C. And then we OR these two things together. And we come up in the end with, I'm just going to put some brackets in here. Or B bar C. And just one thing to remember here as well, the order of things doesn't really matter. So that is the same as that. The order does not matter. Okay? And we can verify that in a couple different methods. We can basically just plug in the numbers and work that through to figure out the truth table if we want, or we can plug in the numbers into the Boolean expression and try to figure it out that way if we prefer. Okay, so some different ways to figure that out. So that was last week. This week we're going to do some more logic gates. We're going to learn 3 new types of logic gates. They're going to be the NAND gate, the NOR gate, and the XOR or exclusive OR gate. So the NAND looks like this, and the NAND gate is basically just an AND gate then combined with a NOT gate. So we're taking the expression here. This gives us A and B, and we're going to take that result and we're going to flip it, which gives us A and B with a bar over the entire thing. So it's basically inverting the result of this, and this is called a NAND gate, and you can identify this by the little circle that we put there. So that is the NAND. So what that means, if A is on and B is on, then the output will not be on. So that's in words, this is the difference here. And you'll notice that the truth table for this one, for the AND gate, it was this. So this is just the inverse of the AND gate truth table. So that is the NAND gate. This one here is the NOR gate. It looks like this. And again, by very similar thinking here, we have an OR that we are inverting the result of. So we have AB. Here we have A and B. Here we have A and B with a bar over it. So this is basically equal to this. So if A is on or if B is on, then the output is not on. And this is our truth table. And again, you'll notice the truth table for this one was this, basically ones everywhere, and anytime you had a 1, you can get a 1 as a result. In the OR gate, this one is just the inverse of that. So that was the OR gate, the NOR gate. Now we're going to talk about the XOR, so the exclusive OR. So this one's kind of funny. This one's a unique one. This is how we represent it. So it looks like an OR with this little line added to it here. And you'll notice that the plus sign with the circle, so plus with a circle around it, that is the symbol for XOR. So what this means in words, this is the exclusive OR. So this means if A is on and B is off, or if B is on and A is off, then the output will be on. So this is basically one or the other, not both. And you can tell that by the truth table here. So 0 and 0 gives us a 0. Only B gives us a 0. So this is only A gives us a 1. A and B gives us a 0. So it has to be only one or the other. So it's this guy and this guy are the only results, are the only input combinations or input permutations that give us a 1 as a result. So both off or both on do not give us a 1. It's only if we have one or the other. So that makes it the exclusive OR. So it's looking for one exclusive input. Okay? So those are our 3 new gates that we're learning this week. So here's a little exercise for us. You can pause for a minute while you look at these and try to answer them. But what truth tables are these? So we've done 6 gates now. We've got 3 here, 3 on the next slide. So what truth tables do these? I'll give you a minute to think about this. And I'll fill in the answers if you want to pause. So this first one here, we have, it looks like the only thing that gives us a 1 is if they are both on. So that is A and B give us a 1, nothing else does. So that is the AND. This one here, B only, A only give us 1s, neither give us a 0, and both give us a 0. That one is the exclusive OR. This one here, we get 0s, give us a 1, B only, A only, and we don't get anything with both of them on. And this one looks like just the opposite of the first one over here. So that is the NAND. Okay, that's those 3. Here's our other 3. What do we have here? Here's the obvious one in the middle here. Smaller truth table, only one input. It has no B input, only an A input. We should be able to identify that one. Give you a minute. Pause it if you like. But this is the NOT. This one over here. Let's do this one here first. So we get 0s give us a 0. If we have B, or if we have A, or if we have both, that all gives us 1s. That is the OR. And over here, we have a 1 with a 0, 0. That is the only combination that gives us that. You can look, and that is the opposite of this first one over here. That is the NOR. That is the NOR gate. Okay, so that is identifying the truth tables for all these different gates. All right, now we're going to go through some different parts that we're going to use in our labs. So first one here, resistor. Resistor is basically a current limiting device. It limits the flow of current. Resistors are all measured in ohms, which is a unit of resistance. And each of these has a different value for its resistance. So the way that we can identify that, you'll see these little bands on here. Most that we will see have 4. They can have up to 5, I think. But most of will have are 4. The way these colors work, The first two colors are numbers. So in this case here, orange and orange represent 3 and 3. The next color is a multiplier. So in this case, brown represents 10 to the power of 1, so basically 10. So what this means is we have 3, 3, and then a tens. So basically 1, 0. If this was, for example, orange, that would mean this would be, so if it was orange, 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 red, that would actually be 2 zeros. Instead, that would be 3,300. And then this final band here, you can't see it very well, but that's gold. Gold means the tolerance, so this should be accurate. The actual measured resistance of this should be accurate within 5%. So this, you can expect that you'll be within 5% accuracy on this. So this should be, say, I think that 5% of this is about 15 ohms. So this should be anywhere between 315 to 345 ohms if you were to actually measure it. It will guarantee that it'll fall somewhere within there. Okay, so what would I expect you to know from this? I would expect you to know that a resistor limits current, that there are colors on here that actually tell you what that is. I would not expect you to know what the color codes are. All right, realistically, I've never used a chart like this to look things up. If I wanted to know what a resistance was in the lab, I would put a meter on this and figure out what it tells me. And you can just measure the resistance that way. That is a much easier way to do. Now, if you know what this chart is, maybe you just know things off by heart. The other thing is you might know that we always use orange, orange, brown resistors. This will be a common practice when we're actually using the kits, is that you want to pull up an orange, orange resistor every time you use an LED. That's what we use with our LEDs. Okay, so that is resistors. Resistors they're not, the direction of them doesn't matter. If you put them in backwards, it doesn't matter. Other things we use. If we were doing live labs, we would be using the SIP resistor. So single inline package is what SIP stands for. This is basically a package of 7 resistors built into one little package that fits nicely on a breadboard. So we use this in combination with the dip switch a lot. Each of these pins represents a 4.7 kilo ohm resistor. In Tinkercad, we're just using 4.7 kilo ohm resistors to do this instead. So we do not have a Tinkercad equivalent to this, so I'm not really too concerned about the SIP resistor unless we're actually using the breadboards in the lab. The dip switch dual inline package. So there's a couple different sizes of them in Tinkercad that we will use, but this is basically a package with 8 switches in it. So you can see dual inline package, meaning 2 sets of pins. So this pin here and this pin here. So we basically can connect up on our board. We have a bunch of holes on the top side of the board, a bunch of holes on the bottom side of the board, and basically this represents a switch across there. So we have basically 8 switches in a row that give us a nice way to switch things easily on our board. This is what we use to create our logic 1s and logic 0s. That is the dip switch. LEDs and diodes. We use 2 different types of diodes. One is the LED, or light emitting diode. This is a unidirectional device, so it has to go in the correct way. If you use a true LED, like in the lab kit, you'll notice that one leg is longer than the other. So this leg here is longer. That is the positive leg. So you can see here it says longer lead. That is the positive side. So that is the side you need to plug in on the positive side. It will not work if you put it in backwards. It doesn't damage it, but it just won't work. And then basically this lights up when power goes through it. This is obviously a red one, and the brightness depends on how much voltage goes across it. If you put too much voltage across it, it'll burn up and you won't get any light out of it at all. The symbol for a diode looks like that, so it basically looks like an arrow, and that means power flow should go that way, meaning that this is the positive and this is the negative side. So the way that these are done in Tinkercad, they look like this. They have one leg like this, and then one leg looks kind of like that. This here is the positive leg, or the what we represent as the longer leg on the true diodes that we use in on the lab kits. We also use this other type of diode. This one here is the little one that is black with like a silver band on one end there, and we use these to basically limit the direction of our current flow. So typically what we'll do is going to the board and from the board, if this is our breadboard over here, this is going to be our positive row, this is going to be our negative row, and then our power supply or battery, this is the positive here, this is the negative. And basically what we get from that is we have a current loop that goes in this direction and back like that. So it basically goes in through the black side, weaves through the silver side, like that, and that's how you can tell that. So basically current flow goes this way, and what happens is that prevents you from ever wiring things backwards, so that you can't if you put these in correctly, you cannot get things going backwards in your system, which is a good thing to do. Which is a good thing to prevent happening, I should say. All right, and then our final thing is the actual chips themselves. The ICs, or integrated circuits. So they look like this. They are about the size of your thumbnail, I'll say. This was your thumb. Your nail's probably about this big. That's about how big they are. They're little tiny things. You will notice here, these are the pins or legs. It looks like a little bug, basically. There's also this little smiley face thing here. That kind of helps you figure out which end is which, so you don't plug them in backwards. So a little smiley face always goes on the left-hand side. And then the writing should be facing towards you as well. The important things on here, this 74LS, I think the ones we use in Tinkercad are 74HS. That's just a different characteristic, but this 08 here, that indicates what type of gates are on that chip. So for example here, an 08 chip is a 2-input AND gate. And that's how we will identify them. So this diagram here represents how everything is wired inside here. You can see this here, that represents that little smiley face area, so you know the orientation of this. So these are the diagrams. You'll see this on the lab PDF. So these are all kinds of different ones. So the 04 chip is an inverter. The 02 is a NOR. The 32 is a OR. The 86 is an exclusive OR. Okay, lots of different types of chips that we will use. So how do you actually make this work? Like, how do you actually connect it? So if you want to use an AND gate, you would use an 08 chip. And there's a couple things you need to do. To make any of these chips work, first thing you need to do is you need to connect 5-volt power to it to run the chip itself. So pin 14 on these diagrams, you'll see where it says VCC. That means connect 5 volts here. where it says ground, that means connect 0 volts here. So that is typically always pin 7 for your 0 volts, pin 14 for your 5 volts. And then you would wire up the rest of it as you need to. So if you wanted to create this here, you would look on this diagram and see what's available to you. There are 4 different options. Typically we always start down here and work our way around and use up what we need to use. So the inputs on this first gate here are pins 1 and 2. So we would take our signal A and signal B and put them on 1 and 2. Our output would come from pin number 3. So that's what we would connect there. And that's basically what we're doing in the lab this week as well on Tinkercad, is wiring these up and verifying the truth tables for each one. Okay, so we're going to switch gears a little bit now and talk about TTL devices. TTL means transistor logic, and it is a type of semiconductor device. TTL devices operate at 5 volts DC, and this is the type of devices we're going to use in the lab. So we need to understand a little bit about the different logic levels that we're going to encounter. So here's a question for you. Is this tap on or off right now? So a dripping tap like that, is that on or off right now? So an electronic device is kind of like a leaky tap. You want to just think about it that way. So off doesn't mean there's absolutely no current flow at all coming out of a device. It just means that that flow has fallen below a certain level and we're considering that to be off. So to me, I would consider this tap over here, I would say this is off. Even though we have a little bit of a drip going on, I would call this off. Similar, I would say this is on. We don't know what the maximum flow out of here is, but this looks like a significant amount of water coming in here. I would say that is on. So on might not mean full capacity, but it means that that flow is above a certain level, and that's going to be the same as well with our electronic devices. So when we talk about these chips, they operate between 0 and 5 volts, but that doesn't mean that logic 0 means 0 volts and logic 1 means 5 volts. Things operate within a range. So if we get a logic 1 out of an IC, that voltage can be anywhere from 2.7 to 5 volts. So if we have a gate, so if we have this, and we get a 1 coming out of here, or what should be a 1, this could be anywhere within this range over here. We could read a signal that is anywhere between 5 volts and 2.7 volts. That is going to be considered a logic 1 or on. Okay, so if we have an LED connected to this, that could mean we have a very bright LED. It could mean we have a kind of dim LED, but it's still on. Okay. Now, similar for a logic 0 doesn't mean we're going to read absolute 0, no power, nothing leaking out of it. There will be some leakage coming out of that even when it is in the off state. And that could be as high as 0.4 volts. So our off signal could be anywhere within this range here. So it could be anywhere between 0 and 0.4 volts on an off signal. We should never get anything that falls in between there. So we should never get anything in this range. If our device does produce something in this range here, that means that there is something actually wrong with the device. Now, same thing with an input signal. In order to switch one of these devices, so let's say again we have this. In order for me to give this a logic 1, I need to give this a signal that is somewhere between 2 to 5 volts. Okay, that is considered a logic 1. If I want to give it a low signal or a logic 0, I need to give that somewhere between 0 and 0.8 volts. Okay, so I can give it a little bit of voltage, but as long as it's lower than 0.8 volts, you'll still consider that to be a 0. What we can't give it is a signal that is somewhere in this range here. If we do this, and you'll actually see that this happens in the Tinkercad lab that I do, the way that I have it set up initially, where I've got some extra LEDs in there to try to demonstrate something, it ends up cutting the voltage on the input signals down to around 2 volts, and nothing works. Okay, and you'll actually see me fumble around and try to fix that. But what's happening there is I'm giving it input signals that are in this range here, and what happens then is the chip doesn't know what to do with that. It just doesn't operate properly. Okay, so we need to give it a clear, if we want to say we are giving it a logic 1, it has to be in here. If we were giving it a logic 0, it has to be in here. We can't give it something in between. It doesn't know what to do with that kind of in-between range there. Alright, so that is understanding the different logic levels on a TTL circuit. Alright, so let's, we're going to break here and then come back and do some practice problems.